Okay, Mattia, you can start.
You should be able to see the presentation.
Right.
Cool. Okay, so yeah, hello everyone. If you have any questions throughout the presentation, just please, I don't know if they can just unmute or raise the hands or whatever. And so we will have a look at this very long title presentation. But most of all, we will have a look at the design for the FPGA, which I will call from now on gateware, to distinguish it from firmware, because firmware is a bit more software. This is more hardware. And this gateware was designed for the level 0 trigger of one of the experiments at CERN, but we will go through some context in which I will tell you what is the NA62 experiment and the framework in which the gateware is in. And then we will delve into the gateware itself and some analysis of the performance. So let's start from the beginning. What is the NA62 experiment? Now, it is CERN-based, and as you probably know, CERN has 4 main accelerators. The LHC1 is the biggest one, but NA62 is not in that accelerator, is in the SPS, which is the second biggest one, and more specifically is in the north area, and it's an actual cavern of 200 and something meters, in which there is a fiducial zone in vacuum, in which particles interact with some detectors. You can see two pictures of the cavern of the experiment, and more specifically, the gateware was produced for the rich detector, and you can see it here in green. So basically, the rich detector is just this big tank filled with neon, and to put it very easy, particles interact. Probably may know with many of you can be physicists, but let's just do it very quick. Particles can interact with the neon inside the rich and produce some Cherenkov circles that are mirrored by some mirrors and collected by photomultipliers. So the idea of the NA62 experiment is to measure the probability, the occurrence of probability of this branching ratio, which is these specific decays of positive kaons into positive pions known bar, which occurs with a very low probability, 10 to minus 12. And the idea is that the SPS particles are accelerated here, and then here it a fixed target and produce some secondary particles that can decay in this fiducial zone. And the detectors in this zone have 3 main tasks, which are the particle identification, which is actually very redundant. Most of all of the detectors can detect particles in specific ranges or in a redundant way. They have to measure the crossing time in the detector, and with a resolution better than 100 picosecond. And they have to track NA62 has to track the particles from the impact point itself up to the endpoint. The particles rate is quite big. It's around 10 megahertz events, but it is a bit too big. Maybe it was too big at the time of the experiment design. Maybe now it's a bit better, but still the rate is higher than the experiment can record in long data storage. So there is a 3-level trigger architecture to help to reduce the amount of stored data from 10 megahertz events down to 10 kilohertz. And this is done by a 3-level architecture in which each step reduces it by a factor of 10. And the 3 levels are the level 0, which is an hardware trigger, hardware and in FPGA, and the other 2 levels, which is level 1 and level 2, which are software triggers. We will now focus solely on level 0, since the reach level 0 gateway is for the level 0 trigger, and we will not consider level 1 and level 2 altogether. So the level 0 trigger is made by a subset of detectors, which uses just a small subset of information from the detector to produce some small size packets called trigger primitives that are sent to a central level 0 trigger processor, here called level 0 TP. And the idea is to have some precise information in time, discarding all the other information from the detectors, almost all of the other information from the detectors. DL0DP then in turns receives data from a subset of detectors and produces a global trigger for the experiment if predefined conditions are satisfied. The detectors in the experiment have each of the detector have a specific readout board, but most of them share the same one, which is the one that it's here in the right, which is called NA62, which is quite generic, that can be adapted to all of the detectors in specific, because there are 4 slots that can be used to connect daughter cards specific to the detector, so that the same board can be used for almost all of the detectors. The daughter cards are usually for the detectors that we will consider are time to digital converter boards, even though there can be also communication boards or ADC boards or whatever. The daughter cards are then read out and handled by one. Each daughter card is read out and handled by one FPGA, a Stratix 3, and that here we call PP, which stands for pre-processing FPGAs, which does that. Pre-processes the data from the daughter cards and buffer them in a 2 GB DDR2 memory and sends them to a central SL, which stands for Sync Link FPGA, which still is a Stratix 3 FPGA, which combines the input from all the PPs and sends the data to a central PC farm and to the level 0 trigger processor via a quad gigabit Ethernet. To complete everything, there is a credit card PC, which is a slow monitor and slow control of the system. So also the rich detector embeds uses these TEL62 boards to implement the readout, but also the trigger. So in all the FPGAs, there will be some modules that performs the readout and some modules that performs the trigger part. The idea behind the gateway for the level 0 trigger of the rich detector is to produce some clusters of hits inside of that occurs inside of the rich, providing a precise time reference to the level 0 trigger processor by exploiting the full time resolution of the timestamps. The TDCBs in the rich case so then produce a 40-bit timestamp with the proper resolution, and the goal of the gateway is just to cluster these hits and send them to the trigger processor. This is done in multiple steps, starting from the PPs where the preliminary clustering is performed, and then the SL merges these clusters, performs a new clustering, and sends the data to the level 0 trigger processor. In addition to this, there is actually also another communication bus, which here I called Intertel, which implements a 16-bit bus that connects multiple TEL62, specific multiple SLs, in order to have more information from different perspectives in order to reduce the noise of triggers. And the idea is that the gateway should be able to use this Intertel bus to perform a better triggering. So we will go through what were the requirements, and we will go also through the working principles we used for the design of the gateway. So the primitives have to be ordered in time down to 100 picoseconds, which is not very true, but still we could have been used 25 nanoseconds, but at the time the requirement was that the primitives had to be ordered in the full timestamp. The problem was that the TDCBs and the daughter cards were not producing the data time ordered, but we exploited some readout modules sorting that sorted the TDCB data down to 25 nanoseconds. The other requirement was to minimize the delay in the primitives production so that the experiment has some time frames of 6.4 microseconds, and the delay should be less than 5 of these time frames. Translated in FPGA words, it means that all of the modules of the gateways should have a throughput of 1 watt per clock cycle, and that the algorithm should be as fast as possible. The other thing is that since the algorithm of the trigger are inside of the TAD62, which is shared also for the readout modules, the logic occupation should be as minimal as possible. And the last requirement was that the design should be able to use the Intertel bus to improve the trigger accuracy and robustness. The other two working principles that we used is that we wanted to reuse the same modules both for PP and SL as much as possible, so that let's say the time to market was as low as possible, and that we used a common data format among the modules so that the modules can be moved around the gateway as freely as possible. The result of these requirements and working principle is in this slide, in this block diagram, in which there is the architecture of the architecture of the gateway. So let's start from the purple modules. These purple modules are just buffering, which compensates for possible spikes in rates and possible problems in gigabit communication and things. The other thing is that all the modules should use the same common format. So in the PPs, the preprocessing FPGAs, the first module is the data converter, which converts data from the TDCB format into this common format that we call rich format. There is then the data validators, which checks the consistency of the rich format in all of the steps of the algorithm. There is then the clustering module, which is shared with the which is shared in the PPs and is in the cell. This is the actual same module, as well as the average calculator is. Then the last module is the input data merger in the SL, which collects the data from all the PPs and sends them in a single stream to the clustering module of the SL. And at last, the primitive builder, which converts the clusters in a format that the L0TP accepts in input. Before delving in the gateway itself, let's have a look at the common format that we call rich format. It is made of two types of words of 32 bits, identified by 4 bits, with a bit of a redundancy in the sense that we could have used just 2 bits, but in order to separate the words in 2 16-bit words to use the Intertel, we split the identification in 2 blocks of 2 bits each in order to identify if it is a timestamp or a data word, and if it is the first word, the first 16-bit word, or the second 16-bit word. So the two type of words are timestamp and data. The first one is a timestamp for effects with a resolution of 400 nanoseconds, and the other one is the data that describes a cluster with a fine timestamp with a resolution of 100 picoseconds as produced by the TDCBs, the number of hits of the cluster, and the cluster time sum, which is a field that we will see what it does, and it is used to compute the average time of the cluster. So the data converter, the first module of the gateway, converts the TDCB's data into this format, interpreting just the single hits as clusters, with the number of hits just 1, and with a 0 cluster time sum. Since the timestamp has a 400 nanosecond resolution, there are 16 timestamp per experiment time frame, which is 6.4 microsecond, and the format foresees that all the 16 timestamps are produced, and followed by a fake data if there is no data, no cluster, no hits in that specific timestamp. This data is just a cluster with the number of hits 0 and cluster time sum 0, and with a maximum find time equal 1, so that 12 bits at 1. And this is done because to avoid some starvation that we will see in the input data merger, without affecting any of the other blocks of the gateway. The input data merger that is in the SL gateway collects the data from all the preprocessing FPGAs and from the intertel if present, and to build a single stream from the preprocessing FPGAs. To do this, it's just divided in 3 steps. All of the steps are purely combinatorial, apart from the FIFOs, of course. And to merge the 2 fluxes, each one of these blocks checks that reads 2 FIFOs in input and orders data down to 25 nanoseconds. So if the 2 FIFOs are not empty, it just reads the FIFO with the smallest time. If one of them is empty and the other one is not, this can lead to starvation of the data in the FIFOs. And this is where the fake data helps. So let's see that case in which one of the FIFOs is empty, the other one is not. Even if there are no hits, no clusters in a time frame of 6.4 microseconds, there will be at least those fake timestamps and those fake clusters. And in this case, it will help to avoid the starvation of the data in the FIFO. After the 3 steps, there will be just one stream of data as in the single PP one, single preprocessing FPGAs one. This single stream then goes into the clustering module, which is the main module of the gateway, which is still divided in some minor blocks. The first one is the data distributor, which reads data from the TDCBs or the data converter or the SL merger, and writes the data into 16 rows. Each one of the rows takes in input only hits belonging to a 25 nanosecond frame, and there are enough rows to there will always be an empty row in which the data distributor can write. This was mandatory to guarantee the throughput of 1 word per clock cycle of the gateway. Each row then consists of 4 cells that performs the actual clustering, and the clusters are merged together if their time is closer than a programmable time window. There is a problem in this row in case that there are more than 4 clusters in a time frame of 25 nanoseconds. But this means an instantaneous rate of 160 megahertz of clusters, which is not impossible, but still was with a very low probability. So it can happen, but it's not that frequent. The other module of the clustering module is the data collector, which reads data from the rows, converts them in a rich format, and sends them to the next module. The idea of the data distributor is just then to receive data in input and sends them to the proper row. Each row takes into account only hits in a 25 nanosecond time slot. The data distributor sends the timestamp to the proper row. Timestamp is a 25 nanosecond timestamp. And then define time the number of hits of a cluster and the cluster time sum to the cells of the row. The data distributor had to solve these corner cases, to handle these corner cases in which a cluster is spans across 2 of these time slots of 25 nanoseconds. And to do this, it compares the data in input to the biggest cluster of the previous time slot. If the time in input is comparable to that previous biggest, it sends to the previous row, otherwise it sends to the current row. The cells themselves are the ones that that performs the clustering and can do one of these three things. If they are empty, they just store the time in input as seed of the cluster. If they are not empty, they have to check if the clustering in input matches or do not matches the time window from the seed. If they do not match, the cell just passes the input cluster to the next cell. If they do match, they merge the clusters by summing their number of feeds and summing their cluster time sum with an actual weighted average. This means that the time of the input cluster is subtracted with the time of the seed and multiplied by the multiplicity of the input cluster and summed with the cluster time sum of the input cluster. All these checks are performed by the matching block, but the cells also consists of a computing block that computes this computation with an embedded DSP multiplier. The two blocks are then connected by a FIFO to take into account the delays of these multipliers. As we saw, the data distributor has to handle these corner cases in which a cluster is between two of the cluster time is between two of these rows, and because of this, when filling a row, also the previous row can be filled. And this comes in hand when we have to read the rows. The data distributor, when finishes a row, can flush the n-2 row, so that in that case the row just acts as a shift register, passing the number of feeds, the time of the clusters and the cluster time sum to the cell to the right, just like a normal shift register. We also had to take into account the sorting of the clusters, and we did this by embedding dedicated electronics into the cells that uses an 8-bit position field that will be used by the data collector just to quickly sort the clusters by addressing a run. Sort the cluster, each cell has to check that if the input cluster matches, it just has to do nothing. If the input cluster has a time greater than the seed of the cluster seed, the cell increases the position field of the right cell. If the clustering input is has a smaller time with respect to the seed time, it increases the position field of the cell. But let's take this situation into account. All the cells are filled with a cluster, and in input to the first cell we have a cluster that has a time lower than all of the times in all the cells. So as a first step, this cell compares the input time with this seed time and discards the cluster, passes it to the next cell, and increases the position field of this cell. And this is repeated 4 times in all of the 4 cells. The 4th cell also discards the cluster because it does not match with the programmable time window and passes to the cell to the right, which is not present. So the cluster will be discarded. The problem is that all the cells incremented by 1 the position field. So all the clusters that are discarded have to be taken into account by a position subtractor, which subtracts the position field in all of the interested cells. When the row is flushed, the cells write the data into the FIFO, and these data are then collected by the data collector, which is made of 4 steps actually. The first one is the data retriever, which reads the FIFOs and writes them in a sorter, which exploits this position field that I just described. And with this position field, it addresses one of the four position of a RAM, and then the cluster discard can just read out the RAM in order with sorted primitives. The cluster discard discards clusters with multiplicity out of a programmable range, just to reduce the noise from events with multiplicity at lower extremes or higher extremes. Then the last step is to convert the clusters in the common rich format of the gateway. The thing that we had to be careful about was in the data retriever, that in order to maintain the throughput of one word, the clock cycle had to read and that had to react to the empty signal of just two consecutive cycles. Here we see why we chose 16 rows. It was not just by chance. It was just to compensate the possible delays, not the possible, the delays, the latency of a row, which is made by the row depth, which is 4 cells. But since the data distributor can fill 2 of the rows, we have to take into account 2 of these rows. And the full latency was made by the number of cells in a row, the multiplier latency, the multiplier embedded in each cell, and the FIFO latency of each cell. So all in all, there was a latency between the clustering input to the data distributor and the clustering output to the data collector of 14 clock cycles. And that is why we chose 16 rows, so that for every clustering input to the data distributor, there would be at least one free row to fill with this cluster. So going back to the block diagram, there is the average calculator module, which actually computes the geometric average of the cluster time by exploiting the CTS field, the cluster time sum. Because all the cells update the CTS field with the thing that we saw before, with a almost geometric average. The only thing that is left to do to have the actual geometric average is to divide the cluster time sum by cluster time sum by the number of feeds of each cluster. This is done by the average calculator, and that updates the cluster time by using its time and the division between the cluster time sum and the number of hits. It is both in the PPs and the SLs because in order to improve the reference time and to avoid overflows of the cluster time sum, because by not performing the division, this field can overflow, even though the time difference between cluster on average will be 0, but it can happen that this field overflows. And to avoid this type of overflows, we compute the average also in the pre-processing FPGAs and not only in the sync-link FPGAs. So apart from simulation, we also perform dedicated runs to verify the design, and we did it in 2 ways. The first one is the result of the first one is this plot, which is a correlation between the primitives production time, the time of the clusters in the primitives, and the time of the class. And sorry, this one is the next one. It's a correlation between the number of hits contained in the primitives and the number of hits computed offline, while the experiment was triggered by other detectors than the reach to avoid biases of the trigger. From this plot, we see that the correlation is quite good, apart from some data here, but also from this we can compute the inefficiency of the system and the false positive probabilities. The inefficiency is computed as the sum of cases in which the the number of hits in the primitives were 0, but in the offline computation not, and the false positive is the opposite situation, obtaining an inefficiency of just 1.2% and the probability of false positive of close to 0. Let's say. The other result of the performance check was the delay in primitives production, since it was paramount for the level 0 trigger processor to work. And we performed this by comparing the time written in the primitives in the cluster with respect to the time of the production of the primitive. From this plot, we see that the delay is quite stable, and it is between 2 and 3 time frames of 6.4 microseconds. And it remains stable for a full run of a full NA62 run. Since we did not use any detector-related information in the reach, we also used the same gateware as it was in another detector, which was the shot detector, and we obtained the same results in efficiency. But there is also a notable thing here that with a higher rate, because the shot had a higher higher rate of hits production, and with an increase of 15% in rate, we obtain slightly lower delay, even though if it is less stable. Before it was very stable between 2 and 3. Now it goes from 1 to 3, but the delay is lower. We also performed some checks that the system could work with the Intertel boards. We did not test it in an actual run, but all the electronics is there to have this in place in case the collaboration, in case the experiment needs the Intertel boards to work. So all in all, we designed the gateware for the rich detector of the NA62 experiment at CERN, and we used it for the level 0 trigger to reduce the data from 10 megahertz of hits to 1 megahertz of primitives. And we did it in a very generic way, so that the same gateware can be used also for other detectors, the shot as we used, but can be used also for all the detectors that are based with the TAT62 readout board. And that was all from my side.
Thanks a lot, Mattia. Are there any questions for Mattia? Since we are not so many, I can just allow for everybody maybe to just unmute if they want. I actually have a question on slide 19 on your results. I was curious to understand exactly what are the corner cases that can cause. So it's like, I mean, you're getting out of time and then you're discarding it, or what? Because you get this, let's say, an efficiency of the 1.2%.
They can depend on, we just isolated one thing, but because we did not have the full control of the input TDCB data, in the sense that the readout was taking care of that. So there are two possible causes. One is the overflow of the input data, that we just lose some data because they are lost in the readout modules. And the other thing is that since there are only 4 clusters per frame, it can happen that these frames are discarded. We flag it in the end of run comments, but we cannot retrieve it in the it's not considered in this plot. So both the two can explain this inefficiency of 1.2%.
I see. So in this case, these are not actual. I mean, these are simulated data. Data for
they are actual data. Yes.
But then also for the offline case, you shouldn't have these timestamps, no? Because how do
yes, you're right. The first one. Yeah, you're right. The first one reason was not applicable to this. It's just the overflow of clusters.
And are the false positives instead due to the fact that like duplicates or what?
This is something we did not understand actually. The false positive case.
Thank you. More questions? Don't be shy. Francesco?
Yeah, I have a question. Can you say more about those fake data? You said when there is no data,
Yeah.
to avoid starvation, some empty cluster with the time equals 0 is created. Can you explain exactly how that data, what are the conditions that create the data, and how often that happens, and how does it help with the starvation?
Yeah, okay. Then these fake data are used here to avoid that one of the two FIFOs remains empty, because if that is the case, this data merger cannot read data from any of the input buffer, and then in turn does not write data into this FIFO, so that this one is blocked and this one is blocked in turn. So if just one of the reprocessing does not produce data, either because the TDCBs are not producing data or just because we are missing something, this would block all the system. So that's why we designed this fake data, so that they do not impact on the clustering modules, since they have a number of hits 0, cluster time sum 0, and maximum find time. So the clustering module does not see them as actual data, and if they enter other clusters, they do not affect either the time of the cluster or the multiplicity of the cluster, but helps here just to speed up the process of emptying the FIFOs. Because if the FIFOs could be big enough, we could just wait until the end of the run and process data with the time that we want. But since it's not the case, we have to speed up the process of having FIFOs read out 25 nanoseconds per 25 nanoseconds. Is it enough? Do you have any questions?
Thank you.
Thanks a lot, Mattia. So if there are no other questions, let's thanks Mattia again.
Thank you.
Okay, and the next seminar will be in the January. We still haven't decided on the date, but stay tuned. We will announce it with our newsletter together with the announcement of the meeting that will come soon. Thanks a lot for joining. Have a good evening. Bye bye.
Bye.